Step outside tomorrow morning, before 9 o'clock. You don't need to do anything, just stand there for 5 minutes, with your eyes open, facing the eastern sky. Don't stare at the sun. Don't squint. Just let the morning light fall on your face. Now, while you are standing there, a single photon leaves the surface of the sun. It travels for 8 minutes and 20 seconds across 150 million kilometers of empty space. It enters your eye through the cornea, passes through the lens, crosses the vitreous humor, and strikes one specific protein molecule sitting in a cell at the back of your retina. A cell that does not see anything in the way you usually mean the word seeing. That one event sets the timing of every hormone in your body for the next 16 hours. That is not a metaphor. That is the machinery. And I want to show you exactly how it works. Because once you see it, you will never look at sunrise the same way again. Let me show you the architecture first. Because if you do not know what is actually inside your skull, the mechanism is going to sound like magic. It is not magic. It is plumbing. It is wiring. It is chemistry happening at very specific addresses inside your head. You have two eyes, but the eye is doing two completely different jobs that share the same hardware. The first job is the one you know. Photons land on rods and cones in the back of your retina. They get converted into electrical signals. Those signals travel down the optic nerve to the visual cortex at the back of your skull, and that is where the picture of the world gets assembled. Trees, faces, the cup of coffee on the counter, the eye as camera. You learned this in school. The second job, the job nobody told you about, is being done by a completely different kind of cell, sitting in the same retina, mixed in among the rods and cones, but doing something almost no eye scientists suspected existed until very recently. These cells are called intrinsically photosensitive retinal ganglion cells. The name is a mouthful. I am going to call them clock cells, because that is what they do. Clock cells make up about 1 to 2% of the cells in your retina. They contain a special pigment called melanopsin. Melanopsin is most sensitive to a very specific color of light, blue light, peaked at around 480 nanometers, the exact color of the morning sky. Now follow me. When a clock cell catches one of those blue photons, it does not send the signal to the visual cortex. It sends the signal somewhere else entirely. It sends it to a tiny structure deep inside your brain, sitting just above the place where the optic nerves cross, the optic chiasm, about an inch behind the bridge of your nose. This structure is called the suprachiasmatic nucleus. The master clock, about 20,000 neurons, roughly the size of a grain of rice. Every single cell in your body has its own little clock running on a chemical oscillation that takes about 24 hours to complete. But all those clocks need to be synchronized to each other, and they need to be synchronized to the sun. That synchronization is the job of the master clock. And the master clock is set every morning by light arriving from your retina through a thin bundle of axons called the retinohypothalamic tract. There is more architecture. Behind the master clock, deeper in the brain, sits the pineal gland, a small organ Descartes thought was the seat of the soul. Descartes was wrong about the soul. He was not entirely wrong about the gland, because the pineal is where melatonin gets manufactured, and the timing of that manufacture is dictated by the master clock, which is dictated by the photons hitting your clock cells. There is more still. From the master clock, signals run to the adrenal glands sitting on top of your kidneys, to the hypothalamus, which controls your body temperature, to the liver, the pancreas, the gut. The morning light signal does not stop at one place. It branches out, like a river entering a delta, and changes the chemistry of every system it touches. That is the architecture. Now let me show you what the photons actually do. The first mechanism is the one that surprised everyone, including the people who were studying eyes for a living. For about 100 years, the textbooks said your eye had two kinds of photoreceptors. Rods, for low light vision, cones, for color. That was it. Two kinds. Anything else hitting your retina was not light reception, it was just glare. Then in 2002, A researcher named David Burson at Brown University published a paper in the journal Science that broke that picture open. He had been studying a strange population of retinal cells nobody could quite explain. He took these cells, isolated them in a dish, completely disconnected from rods and cones, and shined light on them. They fired. Without rods, without cones. They were photoreceptors themselves. That should not have been possible according to the textbooks. But there it was, on the bench. A third kind of photoreceptor in the human eye. Burson identified the pigment doing the catching, melanopsin. He showed melanopsin was tuned almost perfectly to 480 nanometers. The blue end of visible light. The wavelength that dominates the morning sky when the sun is low and the atmosphere is scattering long wavelengths away from your face. Here is why that detail matters. The atmosphere does not deliver the same color of light all day. At noon, when the sun is overhead, the light coming through your atmosphere is biased toward the full visible spectrum, yellow-white. But at sunrise, when the sun is at a low angle, the photons travel through more atmosphere to reach you, and that atmosphere preferentially scatters short wavelengths everywhere. The result is a sky saturated with blue light from horizon to horizon. Your clock cells are tuned to exactly that color. Your eye, in a very real sense, evolved a sensor specifically for the morning sky. 5 minutes of that morning sky, falling on your open eyes, does the following. The photons strike melanopsin. Melanopsin changes shape. The shape change opens an ion channel. The clock cell depolarizes. It fires an electrical signal down a thin axon that bundles with the optic nerve, peels off before the visual cortex, and lands directly on the suprachiasmatic nucleus. The signal arrives at the master clock. Now here is the elegant part. The master clock responds to the signal differently, depending on the time of day it receives it. If the signal arrives in the morning, the master clock is told, now is the start of the day, begin the morning program. If the same signal arrives at midnight from a bedroom lamp, the master clock is told, still daytime, delay the night program. This is called phase shifting. The master clock is a clock you can wind forward or backward, depending on when you flash the light. Charles Scheisler at Harvard Medical School has spent decades measuring how much phase shift you get for a given dose of light. The relationship is dose dependent. Brighter light, longer exposure, earlier in the morning equals stronger advance of the clock. A single morning of bright outdoor light can advance your circadian phase by about 30 to 60 minutes. This is the phase advance window. Stand in it, your clock moves earlier. Skip it, your clock drifts later, and you become a different chronotype than the one your body was built for. Notice the dose. Indoor lighting, even bright indoor lighting, runs about 100 to 500 lux. That is the unit of light intensity at the eye. A cloudy outdoor morning is around 10,000 lux. A clear sunny morning, looking even slightly toward the sun without staring, can deliver 50,000 to 100,000 lux. A factor of 100 to 1,000 brighter than your kitchen. 5 minutes outside delivers more clock-setting signal to your master clock than 5 hours indoors. That is mechanism 1. The clock gets set. But the same photons doing that job are simultaneously doing something else. And to see what, I want you to follow the signal as it leaves the master clock and races to a small gland sitting on top of one of your kidneys. About 30 to 45 minutes after you wake up, something happens inside your body that has been measured in laboratories for 60 years. Your cortisol level surges. It rises by 50 to 75% above the level it was at the moment you opened your eyes. This is called the cortisol awakening response. It is one of the most reliable hormonal events in human physiology. Almost every healthy person has it. Its absence is correlated with depression, chronic fatigue, post-traumatic stress disorder, and burnout. I know the word cortisol has a bad reputation. Cortisol gets called the stress hormone. That is misleading. Cortisol is the wake-up hormone. It is the molecule that mobilizes your liver to release glucose into the bloodstream, that sharpens your blood pressure, that increases the sensitivity of your brain to incoming sensory information, that gives you the metabolic ignition to actually start the day. You want a cortisol awakening response. You want it big. You want it punctual. Here is what morning light does to it. The signal from your retina, the one we just traced to the master clock, branches. One branch sets the timing of the day. Another branch travels down through the brainstem to the spinal cord, exits at the level of the upper back, and runs to the adrenal glands sitting on top of your kidneys. The adrenal cortex receives the signal and releases cortisol. Without morning light, the cortisol awakening response still happens, but it is blunted, smaller peak, slower rise. Christian Kaiochen and his colleagues at the University of Basel measured cortisol output in subjects exposed to bright morning light versus dim morning light, and the morning light group produced a sharper, larger awakening response. Blunting matters. A blunted wake-up response is a body that thinks it is still partially asleep. Now here is something that matters for the older viewer. As people age, the cortisol awakening response naturally weakens. The signal pathway from retina to adrenal does not transmit as strongly. The master clock itself loses neurons. The adrenal cortex becomes less responsive. By the time you are 65, your morning cortisol surge may be half what it was at 25. And that 50% gap is what people often describe as the morning fog. The slow start. The 2 cups of coffee before they feel human. The person at 65 who has been told they are just naturally a slow starter. Who has been told age makes you tired. Who has accepted that mornings will be muddled. That person is not necessarily a victim of age. That person may simply be no longer giving their adrenal glands the signal they need. The retinas at 65 still have clock cells. The pathway to the adrenals still works. The signal is missing. 5 minutes of sun before 9 in the morning is the signal. The dose-response curve here is also steep. Even on a cloudy morning, the lux delivered to the eye outdoors is between 30 and 100 times stronger than what you get from a kitchen ceiling. Kaioschen's group, measuring salivary cortisol after morning light exposure, found that bright light exposure raised the area under the cortisol curve substantially compared to dim conditions. That is not a trivial change. That is the difference between feeling awake at 8 in the morning and not feeling awake until 10:30. That is mechanism 2. The wake-up hormone gets calibrated. But cortisol is not the only thing the morning light is timing. While the master clock is sending its signal to the adrenals, it is also setting a chemical countdown timer in a completely different gland, and that timer will not go off for another 14 hours. When the master clock receives the morning light signal, it does 2 things to the pineal gland. The first is suppression. Whatever melatonin was lingering in your bloodstream from the night before, and there is always a residual amount, especially if you woke up before your natural rhythm finished its night program, gets shut down. The master clock sends an inhibitory signal to the pineal. Melatonin synthesis stops. Your blood levels drop to daytime baseline within about 20 minutes of bright light exposure. This is one of the reasons morning light feels so cleansing. It is sweeping out the leftover sleep chemistry. The second thing is more interesting. The master clock starts a 14-hour timer. Melatonin has a very specific job. It tells every cell in your body that night has begun. Body temperature drops, immune function shifts, the gut quiets, the brain prepares for the slow consolidation work of sleep. The hormone needs to begin rising at the right moment. Too early, and you are sleepy at 5 in the afternoon. Too late, and you are still wide awake at midnight. The right moment is called dim light melatonin onset. In a healthy adult, it occurs about 14 hours after the morning light signal hits the master clock. Russell Foster at the University of Oxford, who did much of the foundational work on non-image forming photoreception in mammals, has shown that the timing of dim light melatonin onset is anchored almost mechanically to the timing of the morning light signal. Move the morning signal earlier, the onset moves earlier. Move it later, the onset moves later. Skip it entirely, the onset drifts, sometimes by hours, and the body loses track of when night is supposed to begin. This is why people who are stuck indoors all morning often find themselves wide awake at 11:30 at night. They have not given their master clock the wake-up signal, so their pineal has not started the 14-hour timer, so melatonin is not rising at 10 when they crawl into bed. The bed feels right. The body does not feel right. The body is missing its instruction. The mechanism here is exquisitely specific. Melatonin is synthesized inside the pineal gland by the conversion of serotonin, which is converted from tryptophan, which arrived in your bloodstream from the protein you ate. The conversion happens in two enzymatic steps, the rate-limiting one being controlled by an enzyme called arylylkylamine N-acetyltransferase. Activity of this enzyme is suppressed during the day and desuppressed at night. The desuppression begins at dim light melatonin onset. The onset is timed by the master clock. The master clock is timed by morning light. Notice the chain. Photon hits melanopsin. Melanopsin signals the master clock. The master clock starts the 14-hour countdown. 14 hours later, your pineal gland releases the enzyme that converts serotonin into the molecule that tells your body it is night. The whole sequence runs on the photons that arrived at sunrise. That is mechanism 3. The night clock is set. But the photons are not done. While the eye is doing its work on the brain, the same morning sky, at slightly different wavelengths, is doing chemistry on a completely different organ. An organ you may not have thought of as a sensory organ at all. Your skin is not a passive bag holding you in. It is a chemically active surface, constantly performing reactions in response to the light landing on it. It is also, by surface area, the largest organ in your body, about 2 square meters of photochemically active tissue. When morning light, particularly the longer ultraviolet wavelengths, what scientists call ultraviolet A, lands on bare skin, it triggers reactions in molecules sitting just below the surface. One of those reactions releases nitric oxide. Nitric oxide is a tiny molecule, just 2 atoms, but it is one of the most powerful signaling molecules in your body. It relaxes the smooth muscle in the walls of your blood vessels. The vessels widen. Blood pressure drops. Richard Weller, a dermatologist at the University of Edinburgh, has spent his career on this pathway. He showed in a series of careful studies that exposing skin to ultraviolet light lowers blood pressure within minutes, and the effect is independent of vitamin D synthesis. People assume sunlight is good for blood pressure because of vitamin D. Vitamin D may help, but the immediate effect, the one that happens during exposure, is nitric oxide release. The two pathways are running in parallel, in different cells on different timescales, both triggered by photons from the same morning sky. For the person who has been on blood pressure medication for 20 years and has been told to stay out of the sun, this is information that recalibrates everything. Sun is not the enemy of your cardiovascular system. It is, when dosed properly, an ally. There is a second pathway worth knowing about. Light hitting the retina also influences serotonin levels in the brain, possibly through projections from the master clock region to the dorsal raphe nucleus, which is the major source of brain serotonin. Serotonin, in addition to its role in mood, is the precursor to melatonin. Morning light boosts daytime serotonin, which supplies the substrate for evening melatonin. The mood effect and the sleep effect are not separate phenomena. They are the same molecule, used at different times of day. Gavin Lambert and colleagues at the Baker Heart and Diabetes Institute in Melbourne measured the turnover of serotonin in human brains and found a striking correlation with hours of sunlight exposure. Bright days, more serotonin synthesis. Dark winters, less. The pathway is not yet fully mapped, but the mechanism is consistent across primate brains, the chemistry is plausible, and the clinical correlations with seasonal mood change are robust. That is mechanism 4. The skin and the brain do their own photochemistry, in parallel with the eye's photoreception, all of it fueled by the same morning sky. So far we have 4 mechanisms: clock setting, cortisol amplification, melatonin timing, nitric oxide, and serotonin. All 4 happen in the same 5 minutes outside before 9 in the morning. All 4 are dose-dependent. All four shape your physiology for the next 16 hours. Now I want to do something I think is important. Because the temptation when you hear a list of mechanisms like that is to assume they are all equally proven, all equally settled, all equally strong. They are not. Let me pause and tell you as honestly as I can what we actually know. There are 3 layers of confidence you should hold in mind. The first layer I will call pavement, solid, repeatedly tested, mechanism understood at the molecular level, replicated across many independent labs. 3 of our 4 mechanisms sit here. The melanopsin pathway and master clock entrainment are pavement. We have the protein. We have the wavelength. We have the wiring. We have the phase shift dose response measured in hundreds of studies. The cortisol awakening response and its modulation by morning light is pavement. Multiple independent groups using different cortisol assays have replicated the basic finding. Melatonin onset timing is pavement. The 14-hour interval, the role of the master clock, the enzymology in the pineal, all of it is established. The second layer I will call gravel. The mechanism is well supported. The direction of effect is reliable. But the magnitude in real-world conditions and the size of individual variation is still being worked out. The nitric oxide pathway in skin sits here. Weller's work is strong, the molecular chemistry is sound, but exactly how many minutes of which kind of light produces how much blood pressure drop in which kind of person is still being mapped. The serotonin elevation from light is also gravel. The correlation with light is robust. The mechanism in the dorsal raphe is plausible, but the human brain measurements are technically difficult, and the numbers vary. The third layer I will call sand. Interesting. Mechanistically consistent. Often repeated in popular accounts. Not yet anchored to enough hard human data to make confident claims. Specific dopamine elevations from morning light, particular effects on testosterone in men, claims that exact wavelengths boost specific neurotransmitters in specific brain regions. These are sand. Some are likely true. Some are oversimplifications. Some will turn out to be wrong. I am not going to tell you they are nonsense. I am telling you they are not yet pavement. When I say 5 minutes of morning sun does specific things to your hormones for 16 hours, the things I have described as pavement and gravel are the ones I stand behind. The sand layer I leave to future measurement. That is the honest map of what we know. Now let me show you why this matters even more than it appears. There is a multi-billion-dollar industry that exists, in part, because most people do not get 5 minutes of morning sun. Begin with the light boxes. A clinical-grade dawn simulation light box, 10,000 lux, the kind prescribed for seasonal affective disorder, costs between $100 and $300. Anna Wurz-Justice at the Center for Chronobiology in Basel, working with Michael Terman at Columbia, established the clinical efficacy of bright light therapy decades ago. The protocols are well established. The boxes work. The boxes work because they deliver a dose of light to the retina that approximates an open sky on a cloudy morning. They are, mechanically, a synthetic sunrise. Continue to melatonin supplements. The over-the-counter melatonin market in the United States alone runs into the hundreds of millions of dollars per year and is growing. People take milligram doses of melatonin to fall asleep. Doses that are roughly 10 to 100 times higher than the natural amount the pineal would release if its 14-hour timer had been started properly that morning. Some of those people would not need any supplement if their master clock had received its wake-up signal. Continue to the antidepressant market. Selective serotonin reuptake inhibitors work, in part, by elevating brain serotonin. Morning light also elevates brain serotonin by a different and milder mechanism. I am not going to tell you that morning sunlight replaces a prescription antidepressant for major depression. It does not. The dose is different by orders of magnitude. The clinical situation is different. People with major depressive disorder need medical care. But the same biochemical lever, serotonin tone, is being adjusted by morning light, every day, in every healthy person, for free. Continue to the cortisol market. Adaptogenic supplements designed to boost morning energy. Cortisol modulating products. Prescription stimulants for people who cannot get going in the morning. All of them target a system the morning light signal calibrates naturally. The pattern repeats across hormone after hormone. The body has, built in, a mechanism for setting its own circadian chemistry. The mechanism requires one input, bright light to the open eye in the first hour or two after waking. When that input is missing, the body falls out of calibration, and a market of products emerges to provide synthetic versions of the chemistry that was always there. Free, waiting for the signal. I want to be careful with the dose calibration, because I do not want you to walk away from this thinking 5 minutes of sun is going to fix major medical conditions. It is not. A light therapy box at 10,000 lux for 30 minutes is a clinical dose. A morning walk in winter, in a country at high latitude under heavy cloud, is closer to maintenance. A diagnosed depression needs a doctor. A prescription medication exists for reasons, and those reasons do not vanish because morning light shares a mechanism with the drug. What does follow from the comparison is this. The difference between a body that gets its signal and a body that does not is not nothing. It is the difference between a biological system running on its native input and a biological system running blind, hoping that pharmaceutical patches will fill the gap. Some of those patches are necessary. Many of them would be smaller, milder, or unnecessary if the upstream signal were intact. The signal is photons. The signal arrives at sunrise. The signal is free. My grandmother used to say a thing, and I remember the way she said it as I was running out the back door as a boy. She would say, "Get yourself out there. The sun will set you straight." I thought she was being old-fashioned. I thought she meant something vague. Go play. Get fresh air. The usual mother and grandmother instructions you heard 1,000 times growing up. She was not being vague. She was describing, in 5 words, a multi-system endocrine intervention. The sun will set you straight. Set you. Set the master clock. Set the cortisol curve. Set the melatonin timer. Set the nitric oxide release. Set the serotonin tone. 5 separate systems, all calibrated by the same signal, all called by the same word she used. Set. She did not know about melanopsin. David Berson would not publish that paper for another 5 decades after she said it. She did not know about the suprachiasmatic nucleus, or the retinohypothalamic tract, or the pineal enzymology. She knew that people who went outside in the morning felt right, and people who stayed in bed past 9 felt wrong. She knew it from watching. The science arrived later and confirmed the watching. This is how folk wisdom usually works. It is not magic. It is a long, careful observation of cause and effect, passed down across generations, expressed in language that compresses a mechanism into an instruction. Set you straight. 3 words. 5 biochemical pathways. The grandmothers were right. They were always right. The science just had to catch up. So here is what you do. Tomorrow morning, before 9 o'clock, you step outside. 5 minutes is enough. You do not have to look at the sun. You do not have to take off your shirt. You do not have to do anything but be present, with your eyes open, in the morning sky. A photon will leave the surface of the sun. 8 minutes and 20 seconds later it will arrive at the back of your eye, strike a protein you did not know you had, set a clock you did not know was running, and shape the next 16 hours of every hormone in your body. That is the machinery. That is what your grandmother knew. Step outside. 5 minutes. Let the morning find you. If you have your own grandmother's words about the morning sun, write them down for me. I would like to read them.